Hello, everyone. Today I'm Mr. Shoemaker, and today we're talking about what is a force and Newton's first law of motion. Okay, so if you were absent yesterday, if you can please tape in the note sheet from yesterday into your notebook. We'll be filling that out first. And for later on, you'll want to make sure you have the qualitative force diagrams taped in your notebook as well. We'll need those to start our first force free body diagrams later on. It may also be helpful for later on to have the list of forces that we copied from the Nearpod slides on the day of the Broomball lab. Okay, so once you have all that ready, we can get going here. So yesterday we defined what is a force. A force is an interaction between two objects. So a force requires two objects. It can't be, just a single object emanating some field, and we call that a force. It has to two objects. So it's an interaction between two objects. Now, if we are going to identify a force, we need to be able to identify those two things. So many times what we'll say is we'll say um, uh, identifying a force requires identifying a dealer. So a dealer, something that is dealing the force out, and a feeler that is experiencing the force. If we can't identify those two things, we're either not having a force, or we just need to, look at everything, all parts of the interaction. Okay. Now, we'll watch a clip. I'll put that on the next slides. If you want to pause this and jump over to the next clip, we watched a clip on inertia. Newton's first law simply states that an object in motion, so an object in motion will stay in motion unless acted upon by another object. So this is the idea that things are lazy. They tend to keep on doing what they're already doing, okay? Um, so even if you're moving at a constant speed, it takes energy or something to stop that motion, right? So even though it's moving at a constant speed, it's going to keep on moving there until something stops it. This could be friction, this could be something in its way, but something does have to stop it, okay? Same thing for an object in rest. Will stay in rest unless acted upon by another object. Okay, so we can write that here. An object in rest, stay in rest. Unless acted upon by another object. So we did this yesterday. I think it says explaining how you can get away from a moose if it is charging at you. Well, the moose, being so large, has a large amount of inertia. So it will take a lot of energy for it to change its motion, right? So if you move in a zigzag pattern, moving in a zigzag, okay, um, uh, will be hard for the moose because it will constantly have to change its motion. And it does have a large amount of inertia being so big. So this will be very hard, require a lot of energy. Okay. We'll constantly change the motion. Another example is what is the amount of force required to keep a 6 kilogram object that is in outer space moving with a constant velocity of 2 meters per second? So if it's constant velocity, the motion is not changing. So it doesn't require any force to keep going here. So we can circle none. It will keep on going at that constant velocity unless it is acted upon by a force. But to keep it at that motion, we don't need any. Okay, let's take this idea now, moving over to our qualitative force diagrams, okay? Now, some of the most common forces that you'll see for this class are your force of gravity. So force of gravity pulls on anything on Earth. So we usually denote that as Fg. We have normal force, F sub n. Normal force is contact force from a surface, right? And this was in the notes from the other slides. Okay, normal force is contact force from a surface. So something is free falling, it doesn't have a normal force, right? Because there's no surface there. And here we say we want to draw a force diagram for a skater who is moving at constant speed across frictionless ice. This constant speed means the motion is not changing. So I'll put constant motion here. Okay. So constant motion. Now, so that means all of our forces need to be balanced. Okay, so if it's constant motion, all forces should be balanced. Okay, now the first step of actually doing this though is we need to define the system that we're going to be identifying the forces for. Here told us we're doing it for the skater, so we can go ahead and circle the skater. That's our system. Now we want to represent that system as a free particle here, and this particle is representing the skater, so I'll label it here. Now, what is pulling on all objects on Earth is the force of gravity. So gravity will pull straight down towards the Earth. So we can have it an arrow pointing downward. And we want to label this as the force of gravity, so F sub g. And then we also want to be able to label the dealer and the feeler, okay? So this is the force of gravity from the Earth onto the skater. So we go E slash S from Earth onto the skater. Now, if gravity is pulling down, remember all forces must be balanced, so something has to be pushing back up on the skater, and this will be the normal force, the ground. So the ground is going to push back up on her, and this will be the F normal from the ground onto the skater. Okay. There are no forces in the horizontal directions, even though she's moving at a constant velocity. Remember, there's nothing pushing or pulling her at this moment. She's just moving, and she's going to keep on moving, unless there were friction, but here there is not, or somebody stopped her or something. And here that's not the case. Okay. So the second one, we need to draw a force diagram for a softball player who is slowing down. So in this case, it is okay if we have unbalanced forces, right? Because we do have some change in motion, so this is not constant. We can go ahead and circle the system that we'll be dealing with, which is the softball player. We can make a free particle and label this as softball player. Okay. What force is acting on anything on Earth is the force of gravity. This is force of gravity from the Earth onto the player. She's not moving in any direction vertically. So we need something to balance out the force of gravity, and of course that will be the normal force from the ground onto the player. She is slowing down as she slides into base here, right? So what that happens is friction is going to be acting on her this way, okay? And that net force there, that is the direction of the acceleration. And here she is accelerating backwards, remembering the last unit. So this will be the force of friction from the ground onto the player. Okay, that's it. Here, these are balanced, so we can, if we wanted to, we could use congruent marks as best practice here. But this one is not balanced, and that is okay because that corresponds to her slowing down. Okay, we have two more to do. Here we have a chandelier that is suspended from the ceiling by a chain, and we want to do the force diagram for just the chandelier part here. So we'll label this as a chandelier. course, the force of gravity is pulling down. This is the earth on the chandelier. And here the chain is what's pulling it up, so that way it's not moving. And we call that usually the force of tension. Sometimes they call it applied force for certain things. It doesn't matter. As long as you can, for right now, focus on identifying the dealer and the feeler. If you're not sure about what the type of the force is, don't worry so much about that, okay? But this is from the chain onto the chandelier. Okay, number four is quite difficult, just conceptualizing it here, but then we're doing a force diagram for the bucket. The bucket is being pulled up at constant velocity. So we need to have a free particle for the bucket. Here we're having force of gravity from the earth onto the bucket, pulling down, and we'll have the applied force from the rope onto the bucket up here. Notice these are balanced because even though it is moving, it is at constant velocity. So the motion is not changing and we need to have balanced forces. Okay, so thank you everyone for listening and we can now try the scavenger trail.